Hello, this is our 2012 MATLAB project. It was done by Eric Isaacs, Dean Reefer, and Troy Dennison. It has three different functions, and each one has to do with cars' initial velocity and whether they will impact depending on different conditions. Our first program is called rear ending, and the scenario is that you have a car stopped at a stoplight and you are driving in the car and you are approaching the stoplight. You realize that the car is stopped and you hit your brakes, and depending on your initial velocity and your initial distance when you first hit your brakes, will you hit the car or not. So we did everything in feet. So the initial velocity, say you're traveling 100 feet per second and you are 80 feet from the car in front of you and you realize and hit your brakes. If you hit enter, you get your outputs here. So you're traveling 100 feet per second and you're 80 feet from the stopped car, and your final distance is outputted here. Obviously you can see it's a negative number, so you did not have enough time to brake and you have rear-ended the car in front of you. Also, with this program, it outputs a plot. The plot is an XY plot with the y-axis is distance away in feet, in our case it was 80, and then time in seconds until you have impacted the car. The slope is the velocity as it decreases as you approach the car, and this is when it hits the x-axis at that value, you have impacted the car. So about 1.8 seconds after you started braking, you have impacted the car. The code for this is a simple user-defined function. You have your outputs, which is final distance and final velocity, and those are outputs. Your inputs are your initial velocity and initial distance. We define them here, and they tell you what you are, and then we use simple kinematic equations and an if statement to decide whether or not you'll hit your car. If your final distance is less than 0, obviously you have surpassed the car in front of you and you've rear-ended it. Otherwise, you have not rear-ended the car. The plot is, we used a time array to set the parameters for the plot. It starts at 0 seconds, goes up to 20 in the space by 0.1 seconds, uses the slope equation to output the actual slope on the graph, and then also has our X labels or Y labels, and we set the axes to coordinate to the actual part of the problem that you're entering, so it varies depending on what your inputs are, and your title and your legend as well. Our second program is called impact velocity, and impact velocity takes the same inputs that were used in the first program, but rather than calculating the distance or whether you hit it or not, it tells you at what velocity you actually hit the parked car when you impact. The first input is your initial velocity as before. So if you're traveling at 50 feet and you are only 40 feet away, you hit enter, and this is actually a while loop. So if we start at the top, you can see that it loops through. This is the time, so as you're decelerating through time, it tells you the distance you are away as you are braking, and it keeps looping until you get to the very bottom. We reach the parameters of when the distance away is 0 and you have impacted the car. So when distance away equals 0, it has been 7.3 seconds and you're traveling at 39.05 feet per second. So you have rear-ended the car. If we go look at the code, this is our impact velocity. We dimension is a user-defined function, so our output is final velocity and our inputs are initial velocity and initial distance. This is our while loop. We set the time as 0, and as time increases by 0.1 seconds, your distance from the car will decrease, and the parameter is that when distance away is greater than 0, you have actually hit the car, and that's when the loop stops. And these are the kinematic equations that we use, and then the if-then statements for our outputs. Our final program is our reaction time program. This scenario is that we did this in a script, and you have two cars traveling down a single lane road. They are both traveling at the same velocity, and the problem is from the perspective of the driver in the second car, the car that's behind the first car. And depending on your age and the driving conditions, we will be able to calculate whether you hit the car or not when the first car starts braking. So you type in reaction time and you hit enter, and it'll ask you a series of questions. It says you and another car are traveling down the road at the same speed. The car in front of you suddenly hits the brakes. What speed are you traveling at? And this is again in feet per second. Say you're traveling at 100 feet per second. You hit enter and the next question comes up. It says, what was the distance between you and the car in front of you initially? And this is an approximation, of course, but you say maybe 200 feet. You hit enter again, the next question comes up, and this is your age, so this has to do with the person's reaction time. You are 65 years old, and your reaction time is a little bit slower. You hit enter again, and then it asks you what driving conditions you are in. Wet, dry, icy, or dirt. Say you are on a dirt road. You hit enter again, and it tells you whether you've collided with the car or not. In these conditions at your age and these initial parameters, you have collided with the vehicle in front of you. If you want to go look at the code, this is our reaction time code. And we start at the top with our script, and our inputs are your initial speed, you and the car in front of you, your initial speeds, the distance between you and your car is an approximation, and then you enter your age. Depending on your age, we create an if-then statement. If you are below the age of 50, you see the car braking and hit the brakes in about approximately 0.4 seconds. If you're above the age of 50, your reaction time is a little bit slower and you hit the brakes in about 0.6 seconds. This reaction time will affects whether you hit the car or not, because you react sooner to braking than you would have if you were older. Below that, we have different driving conditions. These are all decelerations because you are hitting the brakes. So on a dry, it's just a normal everyday road, you are decelerating at approximately 15 feet per second. Wet roads, you are decelerating at approximately 10 feet per second, which is a little slower, so you're more likely to hit the car. Again, icy is even slicker, so -4, and then dirt is -11. So the person would enter those in and out. This would affect your acceleration. So the road conditions are actually used as decelerations in the kinematic equations below. And then we used a if-then statement, and depending on how the above equations relate, you will hit the car in front of you, and if it goes through all of these and through none of these relationships, you hit the car, then you have not ended up hitting the car in front of you. And from the one we did, you ended up hitting the car. You could re-enter and do another one if you wanted to try again. You could say that you were traveling at only 50 feet per second and the car in front of you was 200 feet away. Your age is 20, so you react pretty quickly, and the driving conditions are wet, so they're a little slick. But because you're going slowly and so far away, you have not collided with the car in front of you. And that is our program.